Hello and welcome to another video. Today I'm going to be speaking about partial derivatives. So you might know derivatives from my previous videos on Calculus 1. If you don't know what a derivative is, I urge you to go check them out. Essentially, they're the tangent or the rate of change of our function or graph. Now with partial derivatives, we are in 3 dimensions. Here we were only in 2. So it's kind of unrealistic because everything in the real world is in 3 dimensions. So that's why we created partial derivatives. And I ask you the question, how do we derive our functions, or better said our surfaces or multivariable functions in 3 dimensions? You can pause the video and try and figure out yourself, or you can just try with me. Now, essentially what we're going to do is we're going to try and simplify the problem for ourselves. So we're going to hold one of the variables constant. In this case, I held z constant. I'll just show you where I held it constant. I held it at, let's say, some specific point like 0.5. I held it constant and our z didn't change at all after that. So I cut through my surface and I got some sort of so that is my y and this is my x, and I got some sort of graph or function that goes something like that, and I can sort of know how to deal with that. So now I'm going to show you how we derive how we do partial derivatives. So if we have a multivariable function, x squared plus 5xy plus yz. Now we are going to derive it according to one of our variables, so I'll say according to x. So we hold the other variable constant. So that we just limit it to 2 dimensions and then we just deal with it like regular derivatives. So we imagine that y is a constant and z is a constant. They do not change. They stay constant. Just like our numbers in our regular functions. So let's say f of x. And let's say we have the function f of x, x plus 5, where 5 would be our constant. Now, our z and y are our constants in this case. So, we're going to derive this. It's easy, 2x plus 5 is a constant, y is a constant. What happens when we derive a constant? So let's say we have the derivative of 5x. How do we derive this? Well, it's 5 because of our x. So you can think of y as a number. Let's say it's 2, so then we would have 10x, and the derivative of 10x would be 10. So in this case, it's going to be 5y, and here it's just going to be 0. They're both constants. Now we have to derive for our other variables. 0 plus 5x, both are constants, plus z. Now partial derivative of, according to z, 0 plus 0 plus y. So here we kept z as a constant, and obviously our function was changing according to our y-axis and our x-axis. So that means it definitely wasn't this. It was either this one where z was constant, or this one where z was constant as well. You can figure out, or you can try and figure out which one of these it was and let me know in the comments. So again, usually we get really crazy functions in 3 dimensions. It's much harder than in 2 dimensions, but that's how the real world works. And we sort of color our functions to tell where our function is changing values really fast and where it's changing values really slow. Similar to like when you are looking at a map for hikers. So let's say you're trying to get to Mount Everest or somewhere. There's going to be points where the ascent is not that steep, so your hill is kind of like it's not getting too steep too fast. And places where it goes really crazy, where it gets really steep really fast. So those places would be, let's say here, and let's say less steep places. This is like medium steepness, would be around here. And so you could tell which points where your hill gets really steep really fast, where your function changes values really fast. We would also call this the steepest point, or the place where your function changes the most is called the gradient, and it's denoted as nabla from the Greek letter. That's all for today. I hope you liked the video. Please like, share, and subscribe. See you guys next time.